Welcome. So, you've got these things called autoencoders, and they're amazing at one thing, copying data. But here's the real question. How do we force them to actually learn something useful in the process? Today, we're going to dig into two really clever strategies that do exactly that.
Okay, let's just jump right into the core challenge here. We're trying to make a machine that's literally designed to copy, to, well, learn something meaningful along the way. How do you stop it from just taking the easy route and learning nothing at all?
To really get why the solutions are so smart, we first have to understand the problem. We need to see why just copying is such a tempting and, frankly, useless trap for these neural networks.
All right, so here's your basic autoencoder. It's really got two main parts. You've got the encoder, which takes the input data and squishes it down into a much smaller representation. Then you've got the decoder, which takes that compressed version and tries to rebuild the original input perfectly. Simple enough, right?
Well, here's the catch, and it's a little counterintuitive. What happens if we give the network too much power, too much freedom? It can actually get kind of lazy and learn a trick that's completely useless to us. And this right here illustrates the problem perfectly. The network can just learn to be a flawless copy machine. It figures out how to pass the input straight through to the output without breaking a sweat. So it gets a perfect score for copying, but it learns absolutely nothing meaningful about the data structure. And that, of course, defeats the entire purpose of doing this.
Okay, so let's get to our first solution. This one is really clever because it prevents that lazy copying by changing the actual structure of the network itself.
This is what we call an undercomplete autoencoder. And really, it's the most straightforward way to stop that perfect copying. You just physically constrain the model. You give it less room in the middle than it has at the beginning or the end.
And you can see that bottleneck right here in the diagram. That hidden layer in the middle, it is intentionally made smaller than the input and output layers. This information squeeze, that's the whole key.
So here's the crucial takeaway. This compression forces the network to make tough choices. It literally can't pass all the information through that tiny bottleneck. So what does it do? It has to learn to prioritize. It has to figure out and encode only the most important, most representative features of the data.
Now this architectural fix, it's great, but it does have its limits. It kind of leads us to a new challenge. What if we need a more powerful, higher capacity model to really capture some super complex features? A small bottleneck just might not cut it.
And that brings us right to our second approach, which is a lot more flexible. See, this one constrains the network's behavior instead of its physical size.
So instead of changing the architecture, we're going to change the rules of the game. We actually modify the learning objective itself, the very definition of what success means for the network, to encourage it to learn something useful besides just making a perfect copy.
And this is what we call a sparse autoencoder. Now notice this, it can actually be overcomplete. That means its hidden layer can be even larger than the input layer.
So where's the magic? It's all in the math, right here, in the formula. We start with the standard loss, which is basically just a score for how well the network is copying the data. But then we add a penalty, this little omega of h, and that tiny addition completely changes the network's entire motivation.
You can think of it like a budget. It encourages the network to represent each piece of data using only a small, specialized handful of its available neurons. So even though it might have this huge capacity, it's forced to use that capacity efficiently and, well, sparsely for any given input.
All right, let's put these two powerful ideas side by side. Let's really nail down how they differ and what makes each one so unique. This table really just distills the whole comparison down perfectly. The undercomplete model? It uses an architectural constraint, a physical bottleneck. But the sparse model uses a behavioral constraint, a penalty in its learning rule. One is all about physical size. The other is all about efficient behavior.
So, if you're going to remember one thing from all this, make it this. The undercomplete model forces the network down a narrow hallway. The sparse model, on the other hand, lets it into a huge room, but tells it to only use a few specific tools. It's a physical limit versus a rule-based limit. And that brings us to the final choice, doesn't it? It all comes down to what you need. Are you looking for the elegant simplicity of an architectural squeeze, or do you need the flexible power that comes from a behavioral rule? The answer isn't just about building a better autoencoder, it's really about deciding how you want your model to learn and to think.